Can you hear to me? If you can hear to me, write yes into the chat box. You can hear to me, write yes into the chat box. Okay, fine. Let's start today's session. Today we are going to learn about crossbar network and shuffle exchange network under interconnection network for multiprocessor architectures. Before starting today's session, I will like to say some points to you. At first, take a notebook and a pen with you. Take notes wherever you think. So today's session will go like first we will watch the tutorial. Then you have to attend a quiz. This quiz is actually not meant for WBT evaluation. Rather, it is going to be your self-evaluation. If you attentively watch the tutorial session, then the quiz questions are hidden there. So take notes whenever possible and then attempt the quiz, and after the quiz we will discuss the questions. So let's start our tutorial session. Uh, no audio. Can you hear me now? Hello. Can you hear me now? What happened? Just let's solve the problem. Hello everyone. In this video, we are going to study about Banyan switches, how they can be used in implementation of interconnection networks. Then we will study about crossbar interconnection network. Then we will study about shuffle exchange interconnection network. So let's start with Banyan switches. And this is the general structure of a Banyan switch, where you can see that there are two inputs and two outputs. A 2x2 Banyan switch has two inputs numbered 0 and 1 and two outputs numbered 0 and 1. Now here is a salient feature of Banyan switch, and it goes like: the Banyan switch has a switching control built into the switch itself. That means the control for the switching has been implemented inside the switching device itself. Now question might arise, how the information which arrives into the switch are routed to two different outputs. That means you must have a way out following which you can route output either towards the output port marked with 0 or to the output port marked with 1. And it goes here: every information unit that comes into the Banyan switch has a header that contains a bit indicating its destination, either 0 or 1. So here is the solution to the problem. Whatever information which arrives into the Banyan switch, there is a bit associated with that information which contains the destination in terms of either 0 or 1. If the switch reads the bit and it has a value 0, then it sends the packet to its upper output. So if the information which has arrived into the Banyan switch contains 0 in its first bit of the packet, then it will be routed towards this output. Now if the first bit of the packet has 1, then this output is routed towards the second output port, that is 1. Now by connecting this simple Banyan switches, different interconnection networks have been implemented. For example, shuffle exchange network, omega network, butterfly network, etc., etc. Now today we will look into crossbar network at first. This is the basic diagram of a crossbar network. This numbers encircled in green circles are basically your processors. Now if you look into this block diagram, you can find that you have 8 processors in your multiprocessor system, and the address of the processors are 0, 1, 2, 3, 4, 5, 6, 7. The salient feature of this crossbar interconnection network is that all the processors are connected with each other via some switching devices. These tiny yellow circles are your switching devices. So have a look into the statement. A crossbar has every node of the network connected to every other node. Now, because any node can send simultaneous message to every other node in the system without conflicts, this network topology is basically non-blocking. You can see that each and every node is connected to each and every node via different paths. So, it can easily be inferred that multiple nodes can simultaneously communicate among themselves. There are no chances of conflicts are there. This topology thus becomes non-blocking. So, for example, say processor 2 is communicating with processor 0. Now, processor 1 wants to make communication with processor 3. So, it can follow the direct path which connects processor 1 to processor 3. In this way, this crossbar switching network becomes non-blocking. However, as there are so many switches and so many connections, it becomes very expensive. It will require very high bandwidth, and not too much scalability will be available here. Why? You can see into the figure that there are 8 processors into your system, but to connect these 8 processors you need 8 square, that is 64 switches to connect each of them with one another. If you count the yellow circles, you will find that there are 64 such yellow circles which basically represent switches connecting two processors among themselves. Now, as a generalization, we can say that if there are n number of processors in your system, the number of switches which will be required to implement this crossbar interconnection network will be n square, and in this way it becomes an expensive type of network. So this was the basic idea behind the crossbar network. Next we move to shuffle exchange interconnection network. This is basically a single stage interconnection network. Now, what is a stage in an interconnection network? It is basically the number of layers of switches which are there in between the interconnected processors. You can see that there is only a single layer of switches here, so this is a single stage interconnection network. Now, how this shuffle exchange interconnection network go? To understand that, let me draw a sequence of processors. Say you have 8 number of processors in your system and whose addresses are 0, 1, 2, 3, 4, 5, 6 and 7. These are basically your processors. So in your multiprocessor architecture, for this example, you have 8 number of processors are there. Now, as a rule, these processors will be connected among themselves, something like this. The processor whose address is 0, it will be connected to itself. Processor whose address is 1, it will be connected to the processor whose address is 2. The processor whose address is 2, it will be connected to the processor whose address is 4. Processor which has 3 as its address will be connected to processor with address 6. Processor with address 4 will be connected to processor with address 1. Processor with address 5 will be connected to processor with address 3. Processor which has address 6 will be connected to the, am I right here? Yes, processor whose address is 6 will be connected to processor which has address 5, and lastly processor 7 will be connected to itself. Now, if you split it up, you can think of this diagram like 0, 1, 2, 3, 4, 5, 6, 7. Just assume that virtually you have 2 layers of processors, and this will give you a better visualization of the connection. Processor 0 is connected to processor 0 processor 1 is connected to processor 2, processor 2 is connected to processor 4, processor 3 is connected to processor 6, processor 4 is connected to processor 1, processor 5 is connected to processor 3, and processor 6 is connected to processor 5, and processor 7 is connected to itself. Now the question might arise is this connection arbitrary, or behind this there is some mathematical formulation available? In our computer science, there is nothing arbitrary. Behind every theory, there are some mathematical formulations available. And the mathematical formulation here is this one. Just have a look at the formula and how it goes like. Basically, on the left hand side, you can see that there are xn minus 1, xn minus 2 up to x0 has been appended one after another, and it is on the right hand side it has been left rotated by a single bit. So how it goes like, say you have a number x2, x1 and x0, you will rotate every bit towards its left, or you will shift every bit towards its left by one position. That means you will shift x0 and replace x1 by x0. Then you will shift x1 to the place of x2. So x1 is here. Now who is on the left of x2? There is nothing. But if you think this in a circular way, x0 is on the left side of x2. So x2 will be brought in place of x0. So if you apply your function to this number, the resultant number sequence will be this. Now, what is this xn minus 1 up to x0? This is basically the binary representation of your processor address. This is the binary representation for the processor address. Now, if you look into this diagram, you have 8 processors into your multiprocessor architecture, and the address of the processors are 0 to 7. They have been represented in decimal format. Now, to apply this formula to find out your target processor or the processor with which you can communicate, first step you have to follow is you have to convert these addresses to their corresponding binary representations. So the address of the first processor is 0 and its binary representation is 0, 0, 0. The address of the second processor is 1. So its equivalent binary representation is 0, 0, 1. The address of the third processor is 2. So its equivalent binary representation is 0, 1, 0. The address for the fourth processor is 3. So its equivalent binary representation is 0, 1, 1. The address for the fourth processor is 4. So its equivalent binary representation becomes 1, 0, 0. The address for the sixth processor is 5 in decimal format. So its equivalent binary representation is 1, 0, 1. The address for the seventh processor is 6 in decimal format. So its equivalent binary representation is 1, 1, 0. And address of the eighth processor is 7. So its equivalent binary representation is 1, 1, 1. If you follow the formula, then the rightmost bit is x0, the next bit, this bit, is x1, and the leftmost bit is x2. Now what you have to do, you have to apply this formulation to your processor addresses. Let me do this. The address of the first processor is 0, 0, 0. If you shift each and every bit one position towards its left, then you get 0, 0, 0. Hence, by following this formulation, we can say that the first processor whose address is 0, 0, 0 can directly communicate with itself only. So what you do, if you follow the connection line, you can see that the first processor is connected to itself only. Then come to the next processor, which has 1 as its address. If you shift every bit by one position towards left, you will get 1, 0, 1, 0. You can see that the rightmost bit, that is 1, has been shifted one position towards left. Then this second bit, which has 0 here, again shifted one position towards its left. Then the leftmost bit, if you shift one position towards its left, it will come to the rightmost position. See into the that the processor whose address is 0, 1, 0 in binary format. Now come to the third processor, which has 2 as its address in decimal format, and equivalent binary representation for the address, that is 2, is 0, 1, 0. If you perform the same left shifting operation for this address, you will get 1, 0, 0 after left shifting. So the processor whose address is 100, that is 4 in decimal format, is going to be the destination processor, or the processor with which this processor with address 2 can directly communicate with is the processor whose address is 4. You can see that in the diagram processor 2 has been directly connected with processor 4. Now come to the next processor, that is the processor which has uh, address 3, and the equivalent binary representation is 0, 1, 1. If you have followed our previous discussion, then you can clearly say that after left shifting you will get 1, 1, 0 as the destination address. That is equivalent to 6. So in the diagram you can see that processor 3 has been directly connected with processor 6. Then let we move forward towards our next processor, which has 4 as its address. So if you do the left shifting operation for this processor, the address for the destination processor will be 100 after left shifting. That is the processor which has 1 as its address in decimal format. You can see that processor which has address 4 has been directly connected with the processor which has address 1. Now let we move forward. Now come to processor which has address 5. Now if you do a left shifting here, then the rightmost bit which has 1 here will be at the second bit position, and this 0 which is at the second bit will be shifted towards the leftmost position, and the leftmost one, this one, will be brought into the rightmost position. That is, the destination address will be, can you see it in the diagram? Yes, it is going to be processor which has 3 as its address. So for processor 5, it can directly communicate with processor 3. Now come to the 7th processor. 7th processor has 6 as its decimal address, and equivalent binary representation for the address is 110. So if you do the left shifting, you will have 1, 0, 1 as the destination address, and equivalent decimal representation is 5. So processor 6 has been directly connected with processor which has 5 as its address. Then come to the last processor into our structure. It has 7 as its decimal address, and it has an equivalent binary representation of 111. Now if you do the left shifting here, after left shifting the destination address will be 111. So this 7th processor can communicate with itself only. So this was the making of shuffle exchange network. If you have followed the discussion, now you know how to connect different processors among themselves by following shuffle exchange interconnection network theory. So, this was the discussion about the construction of shuffle exchange network. Here, another thing which I will like to mention is the length of address space. If you look into this diagram, you can find that in its binary format, the length of each and every processor has been 3. For example, 0. The processor whose decimal address is 0 can be represented with a single digit binary number 0. The processor which has 2 as its address, the equivalent binary representation can be done with a 2-digit binary number, that is 10. However, for all the cases, you can notice that we have used 3-digit long binary number to represent all the addresses. That was because you can see that among all the addresses, 7 is the largest value here. Let me encircle it with another color. Now, if you convert 7 into binary number, then it is going to be 1, 1, 1. So, the length of 7 is 3. At the same time, for any binary representation of the addresses into the whole diagram, this is the maximum length of the address of some address present into our shuffle exchange network. So just for all the processor addresses, assign 3 as the length of address space. And this is the idea of finding the length of address space in binary format. Now what we have to do now is you have to go to Google Classroom. Then you can see that under quiz section there is a interconnection network part 2 quiz. Hope you can see this. Just go to the quiz. I'm making it live now. Sorry, what's happening? Edit, assign. Now I made it live. What you have to do is you have to attempt this quiz right now. All the answers are there into our discussion what we have done, and the time allotted is 15 minutes. 15 minutes. Right now it is 12:13, so we will end our quiz session at 12:18. You can start attempting the quiz now. Do it yourself and hope You can answer all the questions if you have followed the discussion carefully. Here is the URL for the quiz. You can access it directly from the Google Classroom, and onto your screen you can monitor how many of your friends are attempting the quiz or is done with the quiz at the same time. So do it. So until now, we have got one response from someone. So until now, we have got one response from someone. You have only for 4 minutes left, so try to do it a bit faster. So the time is over. For some time, I'm stopping accepting responses. Uh, just before discussing the questions, I would like to mention one thing. So don't forget to write your roll numbers into the chat box for the attendance purpose, as we are near the end of the session. So let's start. The first question goes like, in crossbar network, all processors are connected with each other. If it is true or false or maybe. Now, if you, where is it? Yes, go back to this diagram, you can find that in crossbar network, actually all processors are connected with each other. You can see that it is here. A crossbar has every node of the network connected to every other node. Then, so the correct answer is this, yes. Next, shuffle exchange network has how many stages? Uh, if you have followed the discussion carefully, you will find that it is basically a single stage network. So the correct answer is 1. In shuffle exchange network, in between the processor connections, there is only a single stage of switches, in contrast to omega or butterfly networks, which we will study later on. If you look into the structure of omega network, you can find that there are actually 3 stages of switching devices, but in case of shuffle exchange network, there is only a single stage available. So the correct answer is 1. Is crossbar network blocking? The correct answer is no. It is not blocking. It is a non-blocking type of network. So again, you can find it here. Let me erase this thing here. Because any node can simultaneous messages to every other node in the system without conflicts. This network topology is non-blocking. So the correct answer is no. Again, then let me move to the next question. 2 by 2 Banyan switches has how many outputs? If you have followed the diagram of 2 by 2 Banyan switch, then you can see that there are basically 2 outputs. In 2 by 2 Banyan switch, there are 2 inputs and there are 2 outputs. So you can clearly say that the number of outputs is 2. Then let me move to the next question, which goes like, in Banyan switch, switching controls are built into the switch itself. You have to tell if the statement is true or false, yes or no or maybe. Now, here it is clearly written that the Banyan switch has a switching control built into the switch itself. So it implies that the routing of outputs towards to different ports is controlled by the controller implemented inside the switch itself. So your answer is going to be yes here. Next question. If the packet that has arrived into Banyan switch has 0 in header, then the packet goes to upper output or lower output. Now again, let me go back to Banyan switch. Here you can see that if the switch reads the bit, that means header bit or first bit of the packet, and it has value 0, some packet arrived into the Banyan switch, and somewhere here there is its header, and if into the first bit of the header there is 0, it implies that the Banyan switch must send the packet to its upper output, which is marked with 0 in this figure. So your answer is upper output here. Next, suppose you have 16 processors in a shuffle exchange network. So in our example, there were 8 processors into the shuffle exchange network. Now in this question, you are told that in a shuffle exchange network there are 16 processors. The processor with address 1 in decimal number system will be connected to the processor whose address is, now you are given two options, 2, 7 and 8. To solve this, let's see, sorry, take a new page here and let me draw the situations. You have now 16 number of processors in a row in your multiprocessor architecture, and the processors should be addressed from 0 to 15. Now the question is, the processor which has address 1 will be connected to which other processor? To find this, first you have to deduce the length of address space for this multiprocessor architecture. The maximum address value present in the address spaces for the processors is 15. 15 is the highest number for any address here. So let me convert 15 to its equivalent binary number. 1, 1, 1, 1. So for this example, the length of address space is 4. Let me write this. Length of address space is 4. In other words, each and every address in this multiprocessor architecture must be represented by a 4-digit binary number, whether it is 0, whether it is 1, or whether it is 8, or it is 15. So for this, what you have to do, you have to convert the decimal address to its binary address. So decimal address for the processor in question is 1 and its equivalent binary address will be 0001. Now you have to apply shuffle exchange function. That means is it this function to the address space. You have to shift every bit into the address to its left by a single bit, and your address will be, after rotation, 0010. The rightmost bit has been shifted towards its left by a single bit, then the next bit, that means this 0, is again shifted by a single bit towards left. Third bit, that means this 0 is shifted by a single bit towards left, and lastly this bit is shifted towards left by a single bit, and in this shifting process it has come in the place of rightmost bit. Now you can clearly say that this particular processor, which has 1 as its address, is going to be connected to the processor which has address 2 directly. So your correct answer is, sorry, I have done one mistake here. I think it is going to be 2 actually. 2, not 8. Let we come to the next question. Suppose you have 3 processors in a shuffle exchange network. The processor with address 1 in decimal number system will be connected to the processor whose address is, like our previous discussion, it is going to be connected to the processor whose address is 2. Now the only change in this case will be in the length of the address space. In this example you have 4 processors. So the maximum address which is available in this structure is 3. So you need a decimal number with 2 digits to represent the maximum address value. In this case, hence your length of address space will be 2, and the address of the processor which has 1 as its decimal address in binary format is going to be 01. So it is going to be connected with the processor whose address is 10 after left shifting, which means the processor 2. You are going to connect processor 1 with processor 2 directly. Hence your answer is 2. Now let me move to the next question. Suppose you have 8 processors in a shuffle exchange network. The processor with address 6 in the decimal number system will be connected to the processor whose address is 5. If you can recall the diagram, you have noticed that the processor 6 has been directly connected with processor 5 after left shifting of the address by 1 bit. Now, last question. Suppose you have 8 processors in shuffle exchange network. The processor with address 1 in decimal number system will be connected to the processor whose address is 4. So here you can see that there is a mistake once again. This will be basically 2. I have committed a lot of mistakes while formulating the questions in a hurry. So the correct answer is going to be 2 here. So hope you have been able to understand how this shuffle exchange network works. Now, for your future reference, this quiz will be available to you always. To make it available, so responses, accepting responses. Now, what you have to do later on when you will read this module once again, after reading, then attempt the quiz and just see how many of the answers you made correctly. And in this way, you can evaluate yourselves. So, that was all for today. Learn and have safe time in your house. Have a good day. I am going to disconnect the live stream now.